In this video, we are going to talk about cables, and especially about how to connect shield of cables. We are going to have a look on some measurements and how these connections will influence maybe your EMC, EMI, or is this what we are going to talk about, Karen?
Yeah, absolutely.
Okay, you have this kind of setup, and I would like to start with this measurement, the practical example, what is going to happen. So can you show the setup, and we are going to have a look on this experiment. Can you
Okay.
explain a little bit more what we can see here?
So what we've got here is two different ways of looking at what's happening with this system. And it's a really simple system. So what we've got is this is a very, very cheap function generator. So when it generates its signals, it'll also put out lots of noise, which is good for us, so we can observe it. We've got a cable running from the function generator. Right now it's turned off. Cable runs through a current probe, a clamp-on current probe, which is my favorite EMC troubleshooting device because I can just clamp it around cables without having to disrupt or unplug anything. The cable goes into this box. This box is doing basically nothing. It's completely passive. The cables just go to a 220 ohm resistor on the inside. So there's no noise contribution at all from this side. So our current probe is getting fed into a spectrum analyzer. And we can take a look. So a current probe is just, like I say, it's one of my favorite EMC troubleshooting devices. It generates a voltage based on the current that is flowing in the cable that it surrounds. So it's basically using that, the fact that currents generate magnetic fields. That's how it's measuring that, going in the spectrum analyzer. And then it's a little hard to see, but I do have a rod antenna over here, nice little monopole. That's going into one of my other favorite things, which is a tiny spectrum analyzer, a tiny SA. Again, nice and cheap. You can get these for less than $100 on Amazon, and they are, real spectrum analyzers. And so we can see both what's being picked up by, direct currents on the cable and what's then radiating and being picked up by the antenna system.
Oh, this is cool. So before we start doing these measurements, how this can be useful for people? Why we are showing this example?
Right. So there's a lot of debate about what's the best way to shield cables, and in particular, what's the best way to terminate those shields? Because as my, various of my colleagues point out, when you've got a problem with a shielded cable, the problem's almost never in the middle. It's always at one end or the other end. And one example that I saw in the real world, I'd gone to a company that was converting diesel buses, like big city buses, to electric vehicles, which is fantastic. That's a wonderful thing to be doing. But they had run the computer, the CAN network cable for about 2 or 3 meters down the length of the bus, co-routed directly with the high voltage power line to power. And what they were finding is that every time they tried to actually apply, the accelerator to make the bus go, there was so much noise on the computer network that the entire thing shut down. So complete brick. So I came in and I said, okay, can you tell me about the cables? And they're like, okay, here's our twisted shielded pair for our computer network, for our low voltage side. I said, okay, great. Where's the shield terminated? And they said, over there on one end. I said, what about the other end? And they're like, oh, no. We've been told you should not terminate cables at both ends because you'll create ground loops. I was like, could we just try terminating it at the other end? And they're like, no, there's a standard, there's an SAE standard that says don't do it. I'm like, well, but let's just try. And a half hour later, the bus was driving around like normal. But again, I get more pushback on terminating shields at both ends than almost any other statement I make as an EMC engineer.
And I would like to point out, actually, there are many situations when when two or multiple devices are actually connected through shielded cables, especially, I don't know, USB or this kind of, is there, I'm thinking,
Right?
what are
Yep.
the other interfaces, displays or something, HDMI, all
Oh
these
yeah.
kind of standard devices are actually connected through shielded cables, correct?
Yep.
So when someone
And
is designing
sometimes
this
that's
kind of devices which are going to be connected, for example, to PC, then it may be quite important to know how to connect the shield of the cables.
right. And one thing that I don't know how much time we'll have to get into today, but it's something I was talking to Rick Hartley about at the last conference we were both at. Um, when you've got a shielded USB cable, but it's going into an enclosure that doesn't have any metal, so into an enclosure that's just plastic, that shield is not doing you much good. And we'll kind of demonstrate a little bit why that is with this setup.
Okay. So I think we should start with measuring. So before we start, I would like to point out, so the generator is basically some kind of like, it will generate the noise on all the kind of frequencies, yeah? And we will be picking up all these through
So
the...
what I'm going to have it do, and like I say, right now it's off.
Mhm.
I'm going to have it generate a 20 megahertz square wave,
Okay.
and that'll give us 20 megahertz, but then also the harmonics associated with that.
Okay. So we can start. I'm curious.
So the first thing actually that I want to point out is that even though the function generator is completely off, and as I mentioned, everything on the box side is completely passive, this cable's already picking up a significant amount of noise. And so is my antenna over here. And that's the only thing they're picking up is FM radio.
Mhm.
So in the States, FM radio goes from 88 megahertz to 108 megahertz. And it makes sense that this rod antenna, that's basically one of the frequencies that it's designed for, is to pick up FM radio. But then why is our cable doing that? Why is this picking up so much FM radio noise? And the fact is that this is also an antenna, and there's so often, and especially when you're in for like FCC or CISPR 11 kind of testing, consumer electronics, remembering that your cables are also antennas is kind of key to understanding why bad things happen in radiated emissions testing. So in this case, this isn't causing an EMC problem. It's just demonstrating that these things are kind of happening all the time, whether we think about it or not.
Mm-hmm. And I guess if we change the length of the cable, we will be picking up different frequencies.
Yeah, absolutely. Every cable length is going to be more or less sensitive at different frequencies. But the one thing is that it doesn't have to be perfect. So this cable is just as good at picking up over-the-air TV signals up at 180 megahertz. And I was like, oh, I've literally forgotten that over-the-air TV still existed. And I was like, where's all this 180 megahertz noise coming from? I had to look it up on a spectrum calendar. Um, so, when there's enough energy, even a very inefficient antenna can still either pick it up or emit it.
Mm-hmm. Okay, so now you can switch on the generator, or...
Okay, so I switch this guy on, go back channel. So the first thing I'm going to do is set the 20 megahertz square wave.
Okay, I can see something.
Let's just make sure that, yes, right now it's generating, at least it thinks it's generating a pure sine wave. And so we've got a peak that comes up here and a peak that comes up here. And, and there is a little bump at a couple. I've got markers set at 60 megahertz for both of these.
Mm-hmm.
And 60 megahertz has popped up a little bit, so it's not a perfect sine wave, but it's pretty negligible.
Mm-hmm.
Now, as soon as I switch this to be a square wave, the 60 megahertz harmonic is as high as the 20 megahertz fundamental
Mm-hmm.
on both radiated and the conducted measurements.
Even the next one is very high. What is it,
Yes,
80 or yeah?
yeah, that's 80. Yep.
So how the
And
cable
you
is
can,
connected right now? Shield
well,
of the
here's the
cable.
the shield of the cable, so technically this is quote unquote a shielded cable, but the shield is not connected to anything. It's just
Okay.
floating in space. And so it's doing you absolutely no good whatsoever. As much noise as gets picked up or is on the cable is also going to show up on the shield because there's nowhere else for it to go, essentially. And we'll talk a little bit more, I think, about some of the theory behind this, but it's really useful to see that, even though this cable is quote unquote shielded, you're getting no benefit from that shielding whatsoever when it's not connected on either side.
Mm-hmm. So basically, currents are created on this piece of metal, and that's what is happening. These currents, they don't have any other way where to flow. They just go to air.
Yep, exactly. And you can see the more that's flowing on the cable, the more that's getting picked up by the antenna.
Mm-hmm. Okay, so what is the next experiment?
So the next thing to do is, let's see if I can actually do it. Connect the metal of the shield to the metal of the connector.
On one side only.
One side. And what we actually did here was we made the noise worse. The 60 megahertz actually jumped up like I think 5 or 6 dB. And again, both on the spectrum analyzer and both on the conducted and radiated sides. And basically what's happened is that we've taken our shield, which had been acting as an antenna, and we made it a better antenna.
Okay.
So now I will admit one interesting thing, and I'm not sure it's worth unhooking one side to do the other side. If we released this side and only terminated on the box side, the noise would go down because the box is so passive, it's not generating anything. We would have made a worse antenna, essentially.
Mm-hmm.
But now if we terminate on this side as well, and again, I say that like it's easy. Second piece of tape.
So the shield has to be done properly or
Yes.
connected properly.
Yeah. Now, so at these relatively low frequencies, even if I connected this kind of poorly, it would probably still be okay. But right now, as much as possible, I've got basically 360-degree coverage around each shield termination. But what you can see is that, interestingly enough, the 20 megahertz noise went down, but the 60 didn't get touched very much.
Yeah.
And you might be saying, why, Karen, you said that I should terminate shields at both ends. I have terminated my shield at both ends, and I still have all this 60 megahertz noise. What's going on? Well, you think you've terminated it at both ends, but you actually haven't, because you weren't actually connected to the ground plane.
Mm-hmm. Oh, it's gone.
And now the noise is gone. Now we have an actual well-shielded system. So point to point, ground plane to ground plane, and now the noise actually has gone away.
Okay,
But I
so
will note one other point. So the conducted noise on the cable's completely gone away. If you look here, there's still a pretty chunky, it's less, but there is more 60 megahertz noise being picked up by the antenna. That's what's radiating from the box itself, as opposed to what's
okay,
radiating
okay.
from the cable.
Now, I think this is very important. We didn't speak about this aluminum foil on your table.
That is a very good point. So I'm treating this as a ground plane, for what that's worth.
Okay, so
But
basically the generator and also the device is touching the ground plane.
so the box is touching the ground.
Mm-hmm.
And this is a metal box, so it's got full conductivity. But this function generator is housed in plastic. So
That's
it
why
is
you had to
not
use the tape.
exactly. Yep.
But then in real life, what is the ground plane?
That's the thing. In consumer electronics, you usually don't have that. And so this is one of the things. The best shield is the one you don't need. And a lot of times you don't need shielding. And if you have shielding, sometimes it's not doing you any good. Like we saw when I connected on this side, but I wasn't connected to the box and I wasn't connected to the ground plane. I actually just made a worsened or a more efficient antenna, or so I got worse EMC performance because it wasn't connected to anything actually useful. So in a car or on a satellite where you've got a metal chassis, the basic rule to always terminate your shield at both ends is pretty hard and fast. There's almost no reason not to do that. Especially anything relatively high frequency, so anything above like 100 kilohertz, honestly. Um, but again, consumer electronics, medical devices, things where you don't always have the metal chassis of the box or a metal, chassis, a larger structure chassis to connect to, your shielding gets a lot more tricky and it may not do what you hope it will.
Mm-hmm. So basically, when we don't have the ground plane, then the shielding may not be as good as in this example.
Exactly.
And I'm thinking like, is this ground plane basically, or is this setup what we have here, is it basically some kind of like macro PCB track and ground plane in PCB?
You can think of it that way, absolutely. Because the same thing can happen on PCBs. Just usually, when you see that effect, it's going to happen at higher frequencies.
Mm-hmm. But I'm still like then thinking about, so in real life, how do you connect these devices if you don't have this nice ground plane? Then it means shield is not going to be so good. But you have to connect it on both sides. It's just not, there is not just
There's
much what we
nothing,
can do else.
yeah, when there's nothing to connect to, it either is doing nothing or it could actually cause more problems.
Mm-hmm.
And like I say, Rick Hartley and I and a couple other people were standing around at PCB West, and and we're like, man, shielded USB cables into plastic housings. What do you even do with that? And we were all like, yeah, man, that's yep, that's weird.
Okay.
But one of the things that I've been pointing out to folks as I've been doing a lot of presentations, just like this cable was picking up FM radio noise, but it doesn't really matter because I don't have anything here that's sensitive to to FM frequency noise. All these EMC effects with fields and antennas and transmission lines, they're all happening all the time. You actually have to get pretty unlucky to actually have an EMC problem. So you kind of have to have the right combination of noise either being generated by a power supply or being picked up by the environment, and then something that's acting like an efficient enough antenna, and then some victim that's actually sensitive to that. And so, again, the question isn't why do we have so many EMC problems? It's why don't we have EMC problems all the time? Um, and the stars do have to kind of align against you for everything to line up to really cause an issue.
Okay. So I'm thinking about it. So basically, if if the cable is not connected to the ground plane, then it's a little bit. Oh, there was still the 60 megahertz, correct? 20 megahertz was gone, but yeah.
Yep, I take that up a little bit. Heh. Aluminum foil does not love this. But if I separate it out that way, you can see our 60 megahertz came back pretty
Mm-hmm.
strongly.
So it is better, but not the best.
Well, it's interesting because the 20 is considerably better,
Mm-hmm.
but the 60 either wasn't touched or only went down a little bit.
Mm-hmm. So why 60 is still so high?
Almost certainly, this system just reacts better to 60 than to 20. And again, probably because of the dimensions.
Mm-hmm. Okay, so I think now we can go to the slides. What do you have? Or is there
Okay.
anything else what we would like to show on this setup?
No, that's pretty much what I've got. You know, what that setup is really meant to demonstrate.
And now we are going to talk about what is actually happening, yeah?
Exactly. At least that's what we're gonna try.
Okay, you can switch on back your camera and let's
Okay.
let's have a look on the slides.
Okay. So the way I kind of think about this is if there's a concept in shielding called transfer impedance, and even so, transfer impedance is a measurable quantity. Sometimes it's easier to measure and sometimes it's harder to measure. But I think as a concept, it kind of helps explain um, why things are acting the way they are. So if you take the standard equation, V equals I times Z, so Z is your impedance and then current and voltage, we can define a transfer impedance where V is now, actually, it's better to think of it this way. I is the current flowing on the shield, again, whether that's a cable or an enclosure, and V is what's picked up or what appears on the conductors inside the enclosure or inside the cable shield, really. So you can see if there's more voltage developed in response to a given current, then things are not going the way you want, right? You want to minimize this V for your shielding to be the most effective that it possibly can. And to do that, so again, if I is being held steady, the way to make sure V is as small as it can be is to minimize the transfer impedance. And so the thing is, if you can make really good 360-degree metal contacts on both ends, your transfer impedance is going to be as low as it can be.
Mm-hmm.
But if you start to introduce pigtails, if you start to leave one end open, now your transfer impedance is just going to go up and up and up, and you're going to have more voltage show up on your conductors compared to the current that's running on the shield.
On your conductors, it means is the voltage, because I didn't understand, you explained this, but I didn't understand correct. So I understand the current on the shield, yeah, but the voltage is where exactly?
Okay, the voltage is what's being picked up on the wires inside the shield. Yeah, so your shield is surrounding some kind of cable harness, right? So the wires on the inside, you want them to
Oh, okay,
react as,
okay. Because the current is flowing through the shield. Shield is going to generate some fields, and this will create the voltage on the wires inside of the shielded cable.
right.
Okay,
Yep.
okay.
And you can see this. So here on all three of these, the y-axis is transfer impedance, although in this case it's technically ohms per meter, because that's how a lot of manufacturers generate this. Sorry, I should say how they measure it. If you had a perfectly solid shield, um, your transfer impedance starts at just the DC resistance of the connection between point to point to point.
Mm-hmm.
And then as you go up in frequency, you actually get better and better performance. Because again, lower transfer impedance, the smaller you get, the better you're doing. But in a braided shield, which is what I've got on the bench here, you've got all these little strands and you've got little openings between the strands. It's not perfectly optically covered. There your performance gets considerably worse with frequency,
Oh,
because at the higher frequencies it has more and more opportunities to couple into the wires on the inside.
I always thought they are as good as the solid ones.
um Up to a point, absolutely. And the thing is, they're so much more practical than the solid ones. That's why kind of we all use them.
Okay. What is the frequency where it starts going up?
Right around 10 megahertz.
Okay. And the last one is metal tape wrap.
Yeah, so this is where you've got a metallic tape, and actually you see this more than you'd expect in automotive. Again, at least when I was working in automotive, most of the time we were able to get away with not shielding our low voltage wires, just because of good design and really tight control of component EMC performance. But in those cases where we did have to do it, one of the cheapest and easiest ways to do it is you take a metallic tape and you spiral wrap it
Mm-hmm.
down the length of the cable harness. Um, so again, all of these start out where when you're at DC or very low frequencies, your transfer impedance is just equal to the DC resistance that you could measure with multimeter. Here it goes up and up and up, but then it levels out. And the reason it levels out is because of the capacitance introduced by the overlapping sections of tape.
Mm.
And so, capacitance lowers your impedance at higher frequencies, and that's exactly what's happening with the metal tape wrap. So I feel like this is a pretty nice illustration of some of the different physical elements that go into, how these shields work. But you can tell, even if I had a solid shield, if I then had a 5 centimeter pigtail attachment with it's just one little tiny wire, that would add a ton of inductance. Inductance makes your impedance go up at higher frequencies. And so even your solid shield would become much less effective at higher frequencies if it was
Mm-hmm.
terminated that way.
So basically, instead of going like down, it may even go up.
It could go up depending on, again, where, especially what frequency range that pigtail turns out to be resonant at.
Mm-hmm.
That's the one I would worry about.
Mm-hmm.
Um, the other reason that things change at higher frequencies, and again, this is one of those things where in EMC, so often our intuition leads us down the wrong path. I think one of the intuitions that people have about shields in general is that they're kind of like mirrors, that electromagnetic energy will come in and just bounce off of the metal. Um, and that's why you do see people put shields on cables and then not terminate them anywhere, because you wouldn't have to terminate a mirror, right? We don't worry about, oh, is my mirror grounded for optical effects? Um, but as we saw on the bench, it doesn't play out like that in the real world. And amongst the reasons that it doesn't play out like that in the real world is skin depth. So again, our intuition says that we've got current flowing through a conductor like a wire, that it's going to flow equally through all the cross-sectional area of that wire. And that is what it does at DC. But when you get higher and higher frequencies, that current all gets pushed to the outside. It gets concentrated in the outer area of the cross-sectional area of the wire. And, that's a calculatable amount. Um, and so you get actually less sort of communication between what's on the outside of a cable and what's on the inside, or what's on the outside of a shield and what's on the inside of a shield. And again, that's much more dramatic with higher frequencies. And one illustration that kind of shows why does this happen. If you can imagine current being distributed evenly through, again, a wire kind of conductor, as the frequency of this gets higher and higher, it's going to be creating all these magnetic fields essentially. Just like any current in a wire creates a magnetic field around it. But as that's happening inside the conductor, the magnetic fields generate these little eddy currents, which cancel on the inside and add up on the outside.
Mm-hmm.
And so again, this effect gets more and more pronounced at higher frequencies. And by the way, that also is why coaxial coax connector, or sorry, not connectors, coaxial cables can exhibit some of the behavior that they do. So, in a coax, you've got current that flows down the inner conductor and back on the outer conductor. And, and you sometimes hear that outer conductor referred to as a shield, which I really prefer not to refer to it that way because it's an outer conductor. It's part of the intentional conducting system of the coaxial cable. But, if you've got fields on the outside that are inducing currents on the outside, those can be operating just about independently of the intentional currents that are running on the inside of that outer conductor, unless you've got that bad transfer impedance, in which case what's on the outside will show up on the inside, and what's on the inside will show up on the outside, and then you've got more potential for trouble.
So basically what you are saying, the currents which are kind of inside of the outer conductor are more related to the signal which is transferred through the wire inside of and the outside currents can be something different?
Yes, absolutely.
Okay.
I know, shielding seems like it should be so easy. You just wrap something in metal and call it a day. But there's this odd complexity to it that I think catches a lot of people by surprise.
Yeah, I was never thinking about this skin depth actually, exactly as you mentioned. I know about this, but I never was thinking about this in relation to shields.
Well, and the other thing, you can see how tiny these skin depths get, even at relatively moderate frequencies. I mean, I think we can all agree that at this point, 1 megahertz, 10 megahertz, that is not high frequency stuff, right? I mean, you've got your power supplies that are switching at hundreds of kilohertz. Obviously, there's a little bit more of the conductor that they're using at that frequency range, but even then, you're already less than a millimeter. And by the way, I just want to apologize for
Yeah, I
having the
noticed
first
half of
part.
table is in millimeters and half is in mils.
Yeah, having part in metric and part in imperial, but that is the way it showed up in the textbook I was using. So,
But this is good because I think everyone gets the idea what is the size.
but the other thing is that some people have asked me, over time, okay, I'm facing I'm facing an EMC problem. It looks like it's radiating from shielding. Should I just make the shielding thicker or throw another shield on it? And honestly, making it thicker at certain frequencies doesn't do you any good because it's not using the whole depth of the shield. It's only using this little outside volume.
Yeah, I understand.
So that's another thing that you can sometimes double shielding, especially if the double shields are electrically connected together at the ends. It's probably not going to impact your performance much, which is good because it means you don't have to worry about adding the weight and you don't have to worry about adding the cost.
But I'm still then. So what are the solutions? There is only one solution, yeah, for shielding. Connect both ends as good as possible, and that's the best connection.
Pretty much. Now let me jump ahead and show you because, again, people have more questions about this than just about any other thing that I talk about. So let's talk about the times when single ending a shield actually does make sense.
I will make a note so I don't forget. Okay.
Where?
Because there are also sometimes people ask me like when I should use capacitor because I think there are some things which are also related to ESD or also the currents which can flow between different devices because sometimes you may have one device connected to one main or power main and then different device to different power main, yeah, and then they will have different grounds, and then these ground they somehow have to flow through the shield or something.
Okay, ground loops. What you're describing is ground loops, and they are absolutely real if your shielding is well terminated. So what I'm showing here is a fixed installation where, you've got a big cabinet over here and its grounding is literally, a stake pounded into the dirt,
Yeah.
right? Big fixed installation. And, if you've got a cable running, 20, 30, 50 meters, the grounding point for this cabinet, again, it's pounded into the dirt, but the potential difference between, dirt in one corner of the building and dirt in another corner of the building, depending on the humidity and whether it's rained recently, or if it's a wet climate or a dry climate, these could be at very different potentials. And that means that if there's energy in the area, you can start to have current flowing from one side to the other, and through the cable. But this is where skin depth really comes in again, because this is, any of these loops have the potential to pick up noise from their exterior environment. But if your shielding is implemented well, and if you are at relatively high frequencies, then all the noise in this ground loop is going to stay on the outside of the shield and not penetrate into the conductors on the inside.
Mm-hmm.
And that's, again, because you don't have the noise, even though it's flowing on the shield, it's flowing only on the outer volume of the shield. It's not flowing through the whole thing. But I will completely grant at lower frequencies, so especially in audio frequencies, the skin depth obviously is much, much greater. You probably are using all of the conductor, and now noise that is flowing in this kind of ground loop does have the potential to, again, occupy all of the shield and then start to induce currents on the inside. So the main advice is always terminate your shields at both ends, unless you are specifically concerned about stuff down in the audio range.
Mm-hmm.
And again, for these kind of large, massive fixed installations, there's a pretty high potential that noise that you're picking up from the environment could be very, very low frequency.
Mm-hmm. I remember once I had two computers or two embedded boards connected with very long USB cable, and they were in different corners of or in different, even in different rooms. And when the connection happened, then you could hear like all the time. I'm not
Right.
sure if it was related exactly to this, but and I know I remember someone once told me they had these kind of problems with old printers or something, which were using very long cables, and they were on different floors, and they couldn't make it work.
Right. Now, by the way, one thing I do recommend, so if you have those shielded cables, shielded both ends, widely separated, and lifting one end of the shield seems to solve the problem, consider just taking the shield off altogether and see if it makes any difference.
Mm-hmm.
Because again, you might have gotten into a situation where your shield is actually doing you more harm than good, and by the time you lift one end, maybe you don't need it at all.
Mm-hmm. So what is happening in the case when you actually have ground wire inside of this shielded cable? Because sometimes USB, for example, USB has shield, which is also ground, and there is also ground wire inside of this. Is it playing into these kind of situations?
Right. So at that point, any currents that are flowing on ground are going to see two parallel paths, right? One's or multiple parallel paths, depending on your cable harness. And so, they'll go, partway through the inner conductors where they're supposed to go, and partway through the shields, where again, if things aren't terminated well, it can easily turn into radiated emissions.
But is the noise going to be everywhere, or I don't know. I don't know
Pretty
if that's
much.
the right
So,
question, but because it's kind of interesting situation, like you have ground also together with the pins, and it's same ground what is on the shield.
Well, and this is and by the way, I don't know if you've ever picked up or if your viewers have ever picked up a really good textbook. It's called High Speed Digital Design: A Handbook of Black Magic by Howard Johnson. And there's also another really good book that I refer to pretty often, Controlling Radiated Emissions by Design by Michael Mardugian. And both of those, as well as many, many other consultants, basically say if you have plastic enclosures and you don't have anywhere to terminate your shield other than the grounds of your PCB, don't use shields. Just find another way to solve your problem. Your shielding either isn't going to do you any good or could make the situation worse. And and so, one thing that I've seen is, for instance, people running a shield into a box that didn't have any metal chassis. So they grounded it to the heat sink on the inside of the PCB. And again, it just made a better radiator. So you really want to keep your shield connections to something on the outside of your circuitry. Otherwise, you're just introducing more paths for noise to either get out or get in.
So now,
So when I say terminate your shields at both ends, if your only option is to terminate your shield to the board on one or both sides, don't do it. Don't use a shield, because then ground loops will really interfere, have the potential to interfere with your circuitry, because you're just pumping all that noise directly into the circuitry or directly out of the circuitry.
but usually you will have ground wire inside anyway.
I know. Yeah. And again, it comes back to one of the points I was making. To have an EMC problem, you actually have to get pretty unlucky, because there's bad EMC design everywhere. And shielded USB cables going into electronics with no metal chassis is a prime example of that. I mean, how many hundreds of millions of units are in exactly the situation that you're describing, right? And only some of them have EMC problems.
But there may be also difference between, for example, what kind of, how do you power the USB device which is connected through USB cable? Because, okay, sometimes you can power it from the PC. Sometimes you can use adapter. You can use switching adapter with no transformer, or you can use adapter with transformer. So all these will be different situations.
Oh, it makes a huge difference. And that's one of the things, is that at that point, you should be addressing your EMC problems not with shielding, but with filtering or PCB layout or, other best design practices. And you're absolutely right. The power source makes such a huge difference, because I'm sure you and your followers are, well aware of all the challenges that are happening in power electronics. And how, again, switching noise can get everywhere unless you, take steps, very intentional steps to control it. Some companies are really good at controlling it, and in which case, yeah, having a shield there, there's no noise for it to pick up. The noise is all being controlled inside the unit or inside the power supply. Whereas other companies that are more lax about that, again, having a shield there has the potential to just pick up that noise and radiate it, in really bad ways.
I think I've seen, for example, some adapters which, if you measure them, you can actually measure the direct connection between the ground output pin and the ground pin on the main wire, or what is it? On the plug. This one. Like, you can measure direct connection here, with the ground pin.
Absolutely.
Sometimes on some of them they don't have these connections. Transformer power supplies, they may not have this kind of connection. So I think this is something, maybe when people are going to through EMC measurements and they have some kind of problems, they can maybe experiment also with different kind of power supplies or something.
Yes, and there was one thing you mentioned that I wanted to make sure to circle back on. You asked about terminating through capacitors. And that can be a good idea. So if you, but it can be hard to implement. So again, if you've got a full metal chassis, then just terminate straight to that chassis. That's much better than terminating through a capacitor. But in the situation that we're talking about where you don't have that, and for whatever reason, you do still have a shield and you do still need to kind of do something with it. I don't know if you've seen, let's see, find the picture here. No, I thought I had it. Hang on. Here we go. Again, this may not, actually, this certainly won't work for every application, but these filter inserts will give a little capacitor to every pin that goes through them. And then depending on how the connector, connects to everything on the inside of the box, if it does end up connecting to the ground plane of your PCB, then you've got some capacitance to help with high frequency noise, but you've still got DC isolation if DC isolation or low frequency isolation is something that you need. So especially again, when you're talking about audio frequencies. So terminating through capacitance, for one, it can not fix, but it can address the problem where you are concerned about audio frequencies. So you want isolation at low frequencies, but then good connection at high frequencies. And then, to a certain extent, it might be able to help do some filtering, between, again, noise on the inside and noise on the outside, depending on how it's connected. One thing that kind of entertains me about the filter inserts is that I was still at NASA when these first came on the market. And at the time, the NASA folks were like, oh, those will never fly. They're too delicate. They'll never be able to prove all their testing. We don't like them. We're never going to use them. I bounced out to automotive, spent a few years over there, and then came back to aerospace. And, within a few years, everybody was using these. They've really overcome the initial doubts, and they are in pretty wide use in aerospace applications now. So that's certainly an option to make people aware of.
I have never seen this. So you basically place this between the two connectors, or how does it work?
Yeah, exactly. Yep.
So they are very thin, yeah? They just make the connection between the pins and the shield or something. I don't know where.
Exactly. Yeah.
Okay, I think people would like to place their capacitor to prevent the loops, maybe, or something. I think that's the way why they would like to put there the capacitors.
Right. And again, when you're worried about ground loops actually getting into your board, having some capacitors there to at least sort of keep it on the ground plane and not into your circuitry, that can help. But again, the implementation becomes a lot more tricky and a lot more finicky.
So is it problem if these ground loops are there? I guess then it is problem.
So like I say, it's not a problem if ground loops are high frequency noise traveling
outside
on
of
the
the
outside
shield.
of a well-shielded system. It is absolutely a problem if a shield is picking up noise and then connected to the circuitry inside inside a box or on a PCB. Yeah, just don't, if you can at all avoid it, don't terminate shields to PCBs. Just
this is the important point. So where terminate the shields?
And that's
Enclosure?
why, again, that's why a bunch of us were standing around scratching our heads about USB connector shields. Sometimes it's going to be better to leave it floating. Sometimes that'll turn out to be a problem, in which case maybe a capacitor will help. But yeah, it's not a great situation.
But for example, I think all computers, they actually always connect shields directly to the circuit.
I mean, a lot of computers have metal chassis.
Yeah, but these metal okay. Even shields are connected to the ground of the circuit. The chassis is still much better. Okay.
Yeah.
Yeah, and I guess the noise which is traveling outside of the shield will not go inside of the computer, but it will continue on the chassis of the computer.
Exactly.
Okay, maybe I will, once I will maybe start understanding this.
I know it's such a weird, and again, it's one of the reasons why this stuff catches people by surprise during EMC testing when everything goes wrong.
Do you have some, so what do you do actually? You have website, yeah? I think you have your own company, correct?
Yep, I am EMC United. And you know what right now it's just me, but eventually, hopefully, I hope to grow it. But you know what I really focus on, what I want to focus on is education, like you know talking to you today, and giving presentations to different groups and quite a bit of training for people on different EMC related topics. But then also catching things in the design review. So where I really want to get involved in the process is, you know, in that design review phase where, you know, you've laid out a board, but you haven't actually prototyped or manufactured it yet. You still have, it'll still be relatively easy to change a layout if you spot a problem. You know, that's where I think an EMC expert can give the most valuable input. But of course, you know, if that's not the way you went and you end up failing some kind of EMC test and now you need help with troubleshooting, you know, that's the other major thing that we do. Um, and I should add for military and aerospace people, and to an extent automotive, sometimes tailoring your requirements. So, you know, in consumer electronics, you have to meet FCC, and there's not a lot of wiggle room there. But especially for aerospace, you have this big test standard called Mil Standard 461 that's meant to apply to everything from a walkie-talkie to an aircraft carrier. And so, you know, you really need to tailor those tests, the test selections, frequency ranges, and limits to be appropriate for your specific hardware. And so that's the other thing that I can help with.
Mm-hmm. So what kind of problems do you usually see when your clients ask you, or what your clients ask you to solve? Cables, that's something what we are talking about today, but EMC problems are not only about cables. There are much more. So what are the most common ones?
So especially because of the work that I'd been doing in aerospace and automotive for so long, actually the most common thing was radiated emissions coming from cables. Um, that it just again it catches people, and especially when you get into higher power applications. So one of the things that I like to point out, the electric field being generated by a dipole style antenna. Actually, no, the electric field generated by any antenna is dependent on the current flowing on that antenna. It is not dependent on the voltage. It is dependent on the current. And so, you know, if you've got an IC on a board and it's switching, you know, 5 volts or whatever, and it's only drawing picoamps or nanoamps of current, you might have the worst laid out board in the world, but, you know, that's probably just not enough current to cause an EMC problem. But when you've got a clock that's spreading, you know, a particular high frequency signal across the board, that might be drawing microamps or milliamps. And at that point, you're already at a current level that can pretty easily violate FCC or mil standard levels. And then you get into a power supply and you're drawing, you know, hundreds of milliamps to amps. So now you can have more problems. And then you get into an electric vehicle where you're drawing 20 amps or 50 amps or something like that. You know, little design mistakes that you never would have noticed on a smaller, you know, less powerful unit can start screaming at those current levels. And so, you know, that combination of kind of long wiring, um, the switching frequencies of your big power converters, and the fact that those power converters are drawing very large amounts of current, those three kind of combine together in a very unpleasant EMC soup. So that honestly is one of the most common things that we troubleshoot. And depending on what lab you ask, 50 to 90% of all hardware fails EMC testing its first time through. And of the ones that fail, more than 66%, more than 2/3 of them fail either radiated emissions or radiated immunity or susceptibility. So that's definitely the biggest source of problems.
Mm-hmm. So, when the problem is in cables, how can we fix it to minimize the noise going out of this cable? Because, okay, shielding is one thing what maybe we can do, but in the first case, we should not have the noise there, or am I wrong?
Exactly. So again, depending on, whether you're looking at emissions or immunity or what have you, if there's a shield present, the first thing we're going to look at is the terminations. How's it terminated? Is there a way to improve that? The next thing that we will start looking at is inside the board. And, is there a place where we can, or where we need to add filtering? Is there a place where we can improve ground connections? Is there a place where we can change the layout or, well, actually, change the layout's kind of the last thing because I know everybody hates respinning boards. Are there places where we can change capacitor values? So just a bomb change to, again, direct the noise in the places where we want it to go instead of getting out on the places where we don't want it to go. And then the last thing is, again, do we need to change the layout?
Mm-hmm. Okay, and so basically, we also should maybe place some filters or filter circuits where the connectors are placed, correct? Where the signals are going out of the box.
Yep, yeah. Having good EMI filtering right next to your I/O ports is a really good practice to get into. By the way, you notice I didn't say add ferrites. I probably should have, because sometimes that's your only option, and quieting down a cable, adding ferrite is sometimes a way to do that, but that's never going to be our first choice.
Yeah, I remember these situations when we were doing EMC measurements. Then there are two kind of easy solutions. One is buy more expensive cable. The second one is also try the different kind of ferrites. Usually in EMC lab they have this case full of different ferrites, and then they just try one yeah, one by one.
I mean, how often do you see these, right? And don't get me wrong, I've got my own cabinet of ferrites that I can call upon when needed. But for one, they're so ugly. Like every time I see one of those, I'm just like, oh, that's so sad.
But it
But
helps.
when I'm talking about antennas, when I give my class on sort of antennas and why things like cables start acting like antennas when you don't want to, I point out that every time you see this, you know that cable started acting like an antenna
Mm-hmm.
during testing, and that was the fastest, cheapest way to fix it.
Okay, and sometimes we can also change the length of the cable. It also helps.
Yeah, and actually changing dimensions of things, again, it doesn't stop something from radiating, but it basically it can change where it is an efficient radiator. So one thing I should mention is that when you're looking at dimensions, now, if you'll indulge me, I'll give a counterexample in a minute. But when you're looking at dimensions, generally speaking, the most effective when you have a structure, it's going to be most effective radiating something where its length is about a quarter of a wavelength. So for instance, 300 megahertz has a wavelength of 1 meter. So something that's 25 centimeters, roughly in that ballpark, has the best chance of responding to a 30 megahertz signal. Now, again, depending on circumstances and victims and how much power is available and blah, 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 even a very inefficient antenna can still cause problems.
Mm-hmm.
And my favorite example of that, I have a little low-cost SDR USB dongle, and I've been using that as a demonstration of like super cheap tools for troubleshooting EMC. Finally, the connector broke on the one I'd been using, so I got a new one. I just plugged it into my computer to see if it would still, match up with drivers and with the software I was using, and I found that it would. So I started going hunting for frequencies. to bookmark for the next talk I was giving. And I tuned into the local NOAA station. It's a shortwave radio station, and I could hear the broadcaster. It was a little staticky, but shortwave's usually a little staticky, and that's 160 megahertz. But then I went looking for FM. I couldn't find FM at all. And you saw how strong the FM signals are in my area. I was like, what? And then I realized I had not plugged an antenna into the dongle, which explained why I wasn't getting FM, but why on earth was I getting shortwave at 160 megahertz? I took the one that had broken and opened it up, and I realized that there's a 2 centimeter ungrounded heatsink in the USB dongle of the low-cost software-defined radio. Normally, that's like 100th of a wavelength at 160 megahertz, but it was just efficient enough that, given the fact that the entire purpose of that board, that little USB thing, is to respond to RF signals, amplify them, and transmit them, the fact that it was, it wasn't a great antenna, but it was good enough to pick up 160 megahertz. So, when I talk about dimension, certainly, again, that's the most common thing to look at. But sometimes you can end up with unpleasant surprises.
Sometimes you just move it somewhere else.
Sometimes you move it. Sometimes that's all you need.
Yeah.
There's a lot of things that you can mess with.
Okay, when we are talking about this, what do you think about HDMI cables? Because this is the biggest problem every single time.
Yeah, HDMI cables are, again, not fun. So your options for improving your shielding on HDMI are pretty limited. So again, you start looking inside the boards to see if we can improve the filtering. In particular, is one of the first things that you would tend to look at.
So it's not only me who has bad experience with HDMI.
Oh no, HDMIs are notorious.
Okay, do you have something else in these slides what we maybe would like to mention?
I think that really covers the main points that I thought might be interesting for today. Again, this is all part of a full day seminar that I gave just on shielding, just a month or two ago. So but I don't think anybody wants to watch a 6-hour YouTube video on just on shielding right now.
Everybody would like to watch 10-minute video and learn everything what you say in 6 hours. I can guarantee. Okay, so if people have any ideas maybe for different kind of topics what we could talk about, maybe they could leave comments, and maybe we can create another video on different topic.
Absolutely, I'd be happy to.
Okay, thank you very much, Karen, for a very nice example, and I hope people like this.
Yeah, and thank you so much for having me on your channel. I really appreciate the content that you've been putting out there, and I'm really honored to be part of it.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEvel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.